What's up everyone, Level Up STEM here and welcome back to my YouTube channel. Today we will be going over 5 steps to solve any kinematic rigid body problem. And make sure to follow me on Instagram if you haven't already. And like and subscribe to Level Up STEM. Yeah, here we go. So what acceleration A of the collar along the horizontal guide will result in a steady state 15-degree deflection of the pendulum from the vertical? The slender rod of length L and the particle each have mass m. Friction at the pivot P is negligible. Okay, well the first thing I'm going to do on this problem is to draw a free body diagram of the rigid body. It's important to understand which rigid body in this problem we're going to be focusing on. And that's going to be the one we know the most about, and the one also that probably connects different parts of the whole system. So that rigid body is going to be the bar. So in this bar, we have all the forces. We have the reaction force P, both in the y and the x direction. You could draw this as one diagonal P, but I like to split it up into the y and the x direction. And we have both mass of gravities here. We have the weight of the rod and the weight of the mass m at the ball here. And so they're each gonna be mass m each, and that'll be for later. And I also labeled the lengths here, L and L over 2, till we get to the center of mass here, and also the 15-degree deflection. Okay. For the next part, our next step here, we're going to choose a coordinate system to work in. So I think by far the best choice to work for this problem would be the Cartesian coordinate system. And that you'll find that to be the case in most of these rigid body problems. I guess another coordinate system you could choose is the polar coordinate system or else the normal tangential coordinate system. But the Cartesian is probably the best with the I hat, J hat, and K hat directions. And by the way, this K hat circle here means that the positive K hat is coming out of the screen. Okay. So for step number 3, we're going to resolve all our force components. So we have 4 forces labeled on the picture here. And there we go. So I went ahead and combined the px and py into one p. And I gave them I hat and j hat components there. And also the weight of the rod and the weight of the mass m at the ball. Those are both in the negative j hat directions, which is why they have a negative sign out in front of them. And as we know, W equals mg. Okay. So for step number 4 here, we're going to resolve all acceleration components. So we're given in this diagram that A is moving right here. It looks like in the positive I hat direction. So that's exactly what we're going to right here. We have A hat equals A in the I hat direction. Well, okay. So now we know all our forces and we know all our accelerations. So now we can get into the meat of this problem, which is going to be Newton's second law and Euler's second law. So for those of you who don't know, I put them there in the green. So for Newton's second law, we have the sum of the forces equals mass times acceleration. Pretty standard physics problem. You've probably seen this before in a previous physics class. And for Euler's second law here, we have the sum of the moments about point C equals the moment of inertia about C times alpha. And I put an equation for alpha here. I wanted to distinguish this from our already established A, acceleration. So now we know the difference between the two. And also I put the moment equation, which we're going to be talking about later. So we have a moment equals a force cross product with a perpendicular distance. And I'll touch on that later as well. So I went ahead and threw up the information we already solved for in steps 3 and 4. And let's get right into it with Newton's second law. So I wrote out here in the I hat direction, we have the sum of the forces. So just P of x, that's the only one that contains an I hat vector, equals 2m. And I threw in 2m because we have a mass here and a mass there. So our overall mass of the system is going to be 2m times our acceleration. We included that because it has an I hat component right there. And for the j hat version of this formula, we have the sum of the forces, so py minus mg. So I basically took all 3 of these and just threw them there, equals 0, since we have no acceleration in the j hat direction. So that whole term, m times a, is going to go to 0. And we can reduce that to py minus 2mg equals 0. and we can get a value, or an expression, I should say, for Py equals 2mg. Okay, so now we have two equations, this one right here, and also this one right there. But we have three unknowns. We have Px, A, and Py. G is a constant, and we're given mass m in the problem, so we don't have to solve for that. But nevertheless, we still have two equations and three unknowns, so that is still statically indeterminate. So we're going to need to use Euler's second law here. And before we do that, let's establish a center of mass of the entire system. So we have a mass here and a mass there, so we can balance that out by putting one mass of mass 2m in the middle here. And this is going to be L over 4 from our datum right there, or 3L over 4 from our point P up there. So we can express this in the k-hat direction, because that's how moments are expressed, in the k-hat direction, of px I hat, so that's this force right here, cross product 3L over 4 cosine of 15 degrees in the j-hat direction. So that's going to be this distance right here, the perpendicular distance from P of x, or P sub x, excuse me. And so we're going to have that expression for that, and do a similar thing for our Py force. So we're going to have Py j hat, which is this right here, cross product 3L over 4 sine of 15 degrees I hat. And that's going to be this perpendicular distance right there. And we don't need to include the weights in this, since we're accounted for that already as going through the center of mass. And you don't include any forces going through what you're taking the moment about for this expression. And this is going to equal 0, since our alpha here, our angular acceleration, is going to be 0, because it says in the problem will result in a steady state 15-degree deflection. So a steady state deflection means that it's going to be moving at a constant velocity, and we know that to be 0 acceleration. So that's going to equal 0. So we're going to go ahead and solve for those cross products there, and it's going to reduce to that, and it's already in the k-hat direction once you do the cross product, so you do not have to account for that, and that reduces to this equation right here. So now we have three equations, 1, 2, 3, and three unknowns, P of x, A for acceleration, and Py. So three equations, three unknowns. This problem is essentially solved, and you can do the algebra out, and this is going to be your final answer. A equals g tan 15 degrees in the I hat direction, and we know it's I hat because, once again, it's moving in this direction. So that's going to be our final answer. And so these 5 steps to solving this problem can be applied to any dynamic kinematic rigid body problem. This is fantastic for if you're taking dynamics as a mechanical engineering student. I use this a ton, and I'd highly recommend it. So make sure you like and subscribe, and we'll see you in the next video.